My name is Tony Thrill Hill, and this is Thrilling Experiments. Thanks for joining me. You know, ever since I was a small boy, my favorite question was, why? It still is. I love to find out why things happen. That's why science is so awesome. By experimenting, scientists find out why things happen. Today, we're going to perform some amazing experiments with compounds. But first, let's examine compounds. What do you think makes up a compound? Well, a compound is like everything else. It's matter. And if we break down matter into its simplest form, we get the building blocks of the universe. Atoms. Everything is made up of atoms. This table, this shirt, this pencil, even me, and the air I'm breathing. All this stuff is made up of atoms. A substance composed of only one type of atom is called an element. Elements are the purest substances found on Earth. Scientists have discovered 109 elements so far. They are all listed on the periodic table. The periodic table is sort of like a scientific alphabet. Each element is represented by one or two letters. And those elements link together in different combinations to form compounds. Kind of like how you form words from the alphabet. Scientists use these letters to identify chemical compounds. For example, 2 hydrogen molecules and 1 oxygen molecule combine to form a water molecule, or H2O. Water is what we call a compound. All matter is classified as an element, a compound, or a mixture. A mixture is a combination of compounds that does not require a chemical reaction. There are 4 laws that determine whether matter is a compound. First, compounds consist of more than one element. It always takes 2 or more elements to form a compound. Always. The atoms of the elements bond together to create compounds. Look at water. It has 2 hydrogen atoms and 1 oxygen atom. Second, elements must undergo a chemical reaction to form a compound. By the same rule, it takes a chemical reaction to break down a compound to its elements. A chemical reaction means some form of energy is used up or produced. For instance, the sun's energy enables plants to photosynthesize or create sugar compounds out of carbon dioxide and water. The third law of compounds states that a compound has different properties than its elements. For instance, take sodium chloride, or as we know it, table salt. Sodium chloride looks nothing like sodium or chlorine. Sodium is a soft metal, silver white in color, and chlorine is a smelly greenish gas that is poisonous. Together, the 2 elements form a compound. Good old table salt. As you know, salt is a hard, whitish crystal. And certainly isn't poisonous. And the fourth law. Every molecule of a certain compound shares identical properties. Every molecule of water freezes at the same temperature. Looking at water again, you'd see that it freezes at 0 degrees Celsius or 32 degrees Fahrenheit. Great! Now that we have all that straight, I've got some thrilling experiments for you. But remember, as with any experiment, the most important thing is safety. Never attempt any experiment without proper supervision and equipment. And here to help us today is our science expert, June Cifuentes. Hello, June. How are you?
Hello, Tony. Good. How are you?
Great. What's our first experiment today?
Well, Tony, you already mentioned the 4 basic laws of compounds. Do you remember the second law?
I certainly do. It takes energy, or a chemical reaction to form a compound and break it down.
Exactly. So, our first experiment will be to separate the most common compound, water, into its basic elements, hydrogen and oxygen.
Fantastic. Now, what kind of energy are we going to use to break down the water molecules?
That's a good question. In this experiment, we will use electrical energy.
Wait a second. Isn't that dangerous? Mixing electricity and water?
Yes, it is, but we'll only be using 12 volts of electricity from a battery, not 110 volts, which is what comes out of most wall sockets.
Great. Before you begin, be sure to put on your safety gear.
That's right, Tony. Even if you don't think you are working with hazardous materials, it is still very important to use correct laboratory procedures.
All right. We've got our materials. It's time to separate a compound.
Fill the glass jar or beaker about 3/4 full of distilled water. Next, add 1 teaspoon of lemon juice and stir it up.
Now, we're not just making lemonade here. This is real science. You see, pure water is not a very good conductor of electricity. But if there are impurities in the water, whammo! It will do a great job of conducting. Special substances called electrolytes work best. Electrolytes cause the water molecules to break up as the electric current passes through the water. In our experiment, the lemon juice acts as an electrolyte. Hang on, gang. You're about to see something amazing.
That's right, Tony. At this point, you should have your teacher or another adult cut back approximately 6 inches of insulation from one end of each wire. Then strip just enough wire from the other end to hook to the battery, about 1 inch. After that, take the 6-inch bare side of the wire and wrap it tightly around one of the nails 6 or 7 times. Wrap the second wire around the second nail. Now, bend the insulated portion of each wire over the lip of the beaker so that they stay in position, like this. Once they are firmly in position, fill each of your test tubes with water. Now this step is tricky. Take the wire-wrapped nail from the beaker and place it inside the test tube. Holding your thumb over the top, quickly invert the top of the tube into the water. Then release your thumb. That way the water won't spill out. Let's try this one more time with the second tube and nail. There. Practice makes perfect. Be sure to dry your hands off before the final step, or you may get a bit of a shock. Now we're ready to connect the wires to the battery. Connect one end to the positive terminal and one end to the negative terminal.
Did you see that? Bubbles are forming on each rod and then rising up the test tube.
The chemical formula for water is H2O. Do you see how one test tube is filling up faster than the other?
Wow, she's right. This one seems to be filling up twice as fast as the other one. So then, which is the hydrogen and which is the oxygen? Oh, wait, I can figure this one out. In the water molecule H2O, there's twice as much hydrogen as oxygen. So, the tube with less water at the top is hydrogen.
Right. As the elements separate, twice as many hydrogen atoms are released. Now the real question is, which battery post is connected to the hydrogen-filled tube and which to the oxygen-filled tube?
Oh, wow. I never thought of it like that.
The reason we are using electricity to separate the hydrogen and oxygen is because water has a definite polarity. That means one end of the water molecule is negatively charged while the other is positive. That's what makes water such a good cleaning agent. It attaches to things like dirt and carries it away.
The negative post is connected to the hydrogen tube. The negative charge must be attracting the hydrogen because it has a positive charge. And vice versa for the oxygen. Wow, we saw a compound separate into the basic elements right before our eyes. There's always something interesting going on in the world of science. June, what else can you tell us about compounds?
Well, Tony, compounds are grouped by their properties. Acids and bases are the most recognizable groups of compounds. By definition, acids and bases both dissolve in water, but acidic compounds contain hydrogen atoms that have lost electrons. Acids taste sour. Alkaline compounds, also known as bases, dissolve in water, and contain oxygen-hydrogen groups that have gained electrons. Bases taste bitter and are slippery when rubbed between the fingers.
Never touch or taste anything in the laboratory unless instructed to do so by your teacher.
Let's begin our second experiment. To classify compounds, scientists use indicators. Indicators change colors when they come in contact with an acid or base. We are going to use some of these indicators to classify different compounds.
Okay, hey, we have a volunteer.
What's your name? I'm Frankie.
It's good to have you here.
I'm really excited to be here.
Thanks for helping, Frankie. This will be fun. Now, each compound needs to be in a solution. The toothpaste and the baking soda can be safely dissolved in distilled water without changing their properties.
You'll notice that we have labeled each container and are careful never to mix two compounds together by accident. Use a stirring rod and distilled water to dissolve each compound. If you're only using one stirring rod, be sure to clean it between mixings.
For the first part of our experiment, we will use the litmus paper. Blue litmus paper stays blue in the presence of a base and turns red in the presence of an acid. Red litmus paper, on the other hand, stays red in the presence of an acid and turns blue in the presence of a base. So just remember, blue, base. Either color litmus paper will help to classify the compound.
Now, I have a fairly good idea whether some of our compounds are acids or bases, but I'm not so sure about the toothpaste.
Put this on, and let's begin with the baking soda. With the litmus paper, you can classify your compounds one by one. Using the forceps, dip one end of the litmus paper into the solution. Be careful not to submerge the forceps.
Hey, it's blue. That means baking soda is a base.
Now for the toothpaste.
For the next compound, toothpaste, we repeat the process. We've dissolved the toothpaste in the distilled water. We're ready to test.
The red litmus paper turned blue. That means toothpaste is a base, right?
Right. And for the lemon juice, the process is the same. You may even want to alternate the blue and red litmus paper.
Can I try it?
Sure. Just follow the same procedure using the forceps to hold the test paper. Frankie, as you can see, your lemon juice is an acid. Can you see why it is very important to use the forceps? Imagine if you were testing hydrochloric acid.
I sure can.
Now test the vinegar, Frankie.
It's acidic.
Thanks for your help, Frankie.
No problem.
June, we know that we should never taste or touch any chemicals in the lab. So how can we determine how strong acid is?
When you mention strength, Tony, don't forget bases. A strong base can be just as dangerous as a strong acid. Sodium hydroxide, also known as lye, is commonly used to unclog drains. It is very corrosive and should be handled carefully.
Great tip, June. You can never be too careful with strong chemicals.
To determine the strength or concentration of a compound, scientists use a pH test. Let's take a closer look at the pH chart. It is used to measure acidity or alkalinity of a solution. The measurement ranges from 0 to 14. Solutions ranging from 0 to 6 are acidic, with 0 being the strongest. Solutions that are bases or alkaline range from 8 to 14, with 14 being the strongest. A pH of 7.0 is considered neutral. We're going to test our samples for pH. We'll have a volunteer do this one.
Hi, I'm Ashanta.
Using the forceps, insert the pH paper into the solution. Careful now, don't spill any of the solution. Watch as the pH paper changes color, indicating the strength of the first compound. That color can now be compared to the pH chart. Now, all you have to do is identify which shade on the pH chart matches the paper.
This is egg whites, and it shows up on the pH scale at 9.
This is a solution of a common dentifrice.
That's toothpaste to you and me.
Use the forceps to hold the indicator, like before, and dip it into the solution. Notice the change in color. Now, we compare the color with our pH chart.
It has a pH of 7. I sure wouldn't want to use toothpaste with a strong pH like 1.6.
Organic compounds are essential in everyone's diet. They build muscle and give energy. The word organic merely means that the compound contains the element carbon. The foods we are going to test today are all organic compounds, but we will investigate the type of organic compound each food is. There are 3 main types: proteins, carbohydrates, and lipids. It is very important to have all 3 of these in your daily diet. And a volunteer.
Hey, I'm Zack.
First, fill the 12 test tubes about 1/3 full with the following solutions: cooking oil, potato and water solution, raw egg whites, and distilled water. I have labeled the test tubes. This experiment will tell us which of our foods contains a lipid, commonly known as a fat or an oil. Add 5 drops of the Sudan 3 stain to 1 tube of each food product and stir. The tube that turns a deep red color indicates a lipid.
We've just isolated the lipid. It's the cooking oil. Well, that wasn't too hard to figure out. But our next test will show us the carbohydrates. Carbohydrates are the starches and sugars. Our bodies break them down and use them for energy.
Be sure to clean the dropper between solutions, or use a new one. Now, add 5 drops of iodine solution to 1 test tube of each food product and stir. First the potato, now the egg whites. A color change in the range of yellow-brown to blue-black indicates a starch. A starch is a long chain of sugar molecules hooked together. Starches provide longer-lasting energy because they are more complex and take longer to break down.
Look at the test tube containing the potato. The reaction indicates that the potato contains starch. So does that mean that the potatoes contain sugar?
Well, yes. Potatoes contain starch, which is a complex sugar. The starch in potatoes is what makes them a hearty food. Now, for the last portion of this experiment, add 5 drops of Burette's reagent to each test tube to determine which sample is a protein. Again, a positive reaction will create a color change ranging from yellow to blue-violet. But this time, we're using a different reactor.
Look, the egg white solution turned color. Of course, egg whites are an excellent source of protein.
That's right, Tony. The Burette's reagent identified the protein in the egg whites.
Hey, water was the only compound that did not react with the other indicators.
Remember, Tony, the definition of an organic compound is one that contains carbon. What is the chemical formula for water?
H2O, hydrogen and oxygen. Water does not contain carbon, so it is not organic. It is an inorganic compound. Scientists have experimented with compounds since the beginning of time. They found ways of combining compounds to create solutions and products that we use every day.
Let's do some combining of our own. And a volunteer.
Hey, Frankie's back.
Hello. Hey, Frankie.
Hi.
Our first combination of compounds uses dry ice. Dry ice is frozen carbon dioxide, a compound of carbon and oxygen. Make a solution of 5 gallons of water, 1 bottle of root beer extract, and 5 pounds of sugar in a large container and stir it well. You can reduce these quantities if you wish. Just be sure to keep the same ratio of ingredients.
You have to be very careful when handling dry ice because it's so cold it could cause a nasty burn. So, use tongs, gloves, and make sure you use the proper eye protection as well. You wouldn't want any dry ice in your eyes now, would you?
Good point, Tony. Place the dry ice into the solution.
Hey, look at it boil. That's quite a reaction.
Actually, it's not boiling. The frozen carbon dioxide is changing from a solid directly into a gas. You see, the intermolecular forces are not strong enough to hold carbon dioxide in liquid form at normal atmospheric pressure and temperature.
Is the vapor toxic?
The white fog is not the CO2 gas, but rather the condensed water vapor mixed with the CO2, which is invisible. The extreme cold causes the water vapor to condense into clouds and become heavier than the surrounding air. Carbon dioxide gas displaces oxygen and will not support life, so I would avoid breathing too much of it. When the dry ice has stopped reacting, the solution in your container will be carbonated. You have made enough root beer for your entire class.
That's so cool. What's next?
Place several really dirty pennies into a glass bowl. Add 1/4 cup vinegar, an acid, and a tablespoon of salt, a base, to the bowl. The grime, or tarnish on the pennies, is called cuprous or cupric oxide. These oxides are soluble in acid. Vinegar, which is a 5% acid solution, dissolves the oxides on the pennies. The added salt adjusts the strength of the acid and promotes a faster reaction. Mix the 3 together, and after a short period of time, you'll notice the newly combined solution has cleaned the pennies.
It sure has.
To begin, light a candle. While the flame is growing, place place approximately 3 tablespoons of baking soda into a sidearm flask. Add about half a cup of vinegar to the flask and very quickly put the stopper on. Now, aim the arm of the flask at the flame. The resulting compound, CO2, in a gaseous state, will blow out the flame. You have just made your own fire extinguisher.
Wow, compounds are pretty cool.
They sure are. Thanks for your help, Frankie.
Thanks for joining us today. I sure learned a lot. We'll see you next time on Thrilling Experiments.
Bye.
Bye-bye.
Bye.
Bye-bye. I sure do. It takes energy or a chemical reaction to form a compound and break it down.
Exactly.
Yes.
So, for our first experiment,
So, use tongs, gloves, and make sure you have the proper eye protection as well.
well, yes, potatoes can stain